So thanks again to Michael. So I'm very happy that George is here. He's going to give a presentation on content context-aware content. And yeah, the floor is yours. Afterwards, we are going to have a panel discussion, as I mentioned, with George, Michael, and Mark. But now, yeah,
thank you. So, I'm George Kamel. I'm from the University of Surrey. I joined the university actually in 2011, so I've spent five years there. Prior to that, I was actually here in King's College, where I spent 8 years studying for my undergraduate and my PhD. So it's good to be back in the place where I spent most of my life. So my presentation is on context-aware content networking for 5G. So it's really looking at slightly higher layer perspective of how we can intelligently support content delivery in 5G. So firstly, I'll give a small introduction to what content networking is. Hello. And then I'll go through context-aware content networking for fixed networks. And that's where our expertise really started off in content networking as a university. And then I'll go on to how we can apply context networking in the mobile networking area. And finally, I'll just go over some other related open research issues and summarize. So this is a graph you're probably all familiar with and we've seen countless times, and it comes as no surprise that mobile traffic is expected to increase. And Cisco predict that by 2020 we'll see an 8-fold increase in mobile data traffic. And if we break that down into the various applications, we can see that mobile video is taking the majority of the traffic being transmitted through the mobile network. So from 55% in 2015, and that's increasing to 75% by 2020. So for that reason, a lot of the work that we're carrying out, the research, is really tailored towards video delivery. And so that'll be quite a big focus of this presentation. So what is content networking? Well, let's look first at what the traditional networking, how that works. So this is a model really from the 1970s, you could say. And sessions here are maintained, established and maintained end-to-end. And the whole model is related to network resource sharing. So the whole idea is to be able to share resources between different users, but not have the network play any role in how this content is delivered to the user in a quite intelligent way. So it's referred to as a bit pipe. So the flows travel end to end from the content server to the clients. And it's typically transferred on a best effort basis. So we try to prioritize what traffic is important and what traffic is less important, and based purely on prioritization of traffic. And then the next, let's say, evolution of data access came with the introduction of content distribution networks, CDNs. And the aim here is to try and bring content closer to the user. So, and content would be typically strategically located within the network, so that, for example, if there's an advanced knowledge of a football match, then that content could be pre-located or pre-mirrored at a certain server farm which is closer to the users. And so here the content has to travel less to some of the users when that can be achieved. So the next approach is in content-centric, the content-centric approach. So here, the network has an awareness of content. So it knows the kind of content that's traveling through the network. And it's aware of, so in terms of video, if it's high definition video or 4K or whatever, it's aware of all these aspects of the data. And fundamentally, the fundamental change between the IP approach and the content-centric approach is that content is retrieved using a content name rather than an IP address. So we no longer use or try to retrieve data with prior knowledge of the location where the content is stored, but now the network has a greater knowledge of where content is located. And so the user puts in a request to the network for a particular content, and the network itself knows how to deliver that content to the user. And as a result, we can make use of in-network caching, for example. So that allows the content to be brought closer to the user, but in a more, let's say, dynamic approach compared to CDNs, where in CDNs the content would have to be pre-mirrored in advanced knowledge, based on advanced knowledge of where demand will be. However, this is mainly considered for wired networks, and there's been little consideration about how this could be applied in the mobile infrastructure. So throughout the rest of the presentation, I'll give some use cases and explain how this could be leveraged on in 5G. So just to backtrack a bit. So here we've got the host-centric networking approach. So the user would get the IP address of the server hosting a certain object, say object B, in domain B. And then it would make a request to connect to server X and get object B. And each router in turn would route towards the server being requested. And then the data would be delivered back to the user based on the IP routing, traditional IP routing. In the content-centric approach, or the information-centric approach, both are synonymous, the user would ask the network for a particular object. So here it requests object B from router 1, and router 1 would route towards object B through the next hop. It knows about how to reach that object. And it happens to be actually cached in router 4, so it would just deliver the content back to router A along the reverse path of the request. So with the network armed with knowledge of content, it can have better opportunities to engineer traffic and localize traffic to the user, and be able to maybe divert requests to servers which it knows are nearer to the user than the one it could think it's nearest to it. However, there are concerns about scalability for this, because whereas in the IP space, the routing is done based on IP prefixes, and network nodes are addressed uniquely based on a unique IP address. Here, it's the content that has to be addressed uniquely. So the content space is much bigger than the networking space, let's say. So very briefly, I'll just go through what we've done to improve scalability in the fixed network for content-centric networking. So this is a approach we've proposed called CANE. And the idea here is to efficiently disseminate context information to the various network elements, so that the network elements can make informed routing decisions, how best to reach that content. So we want to improve content routing and resolution decisions. So, however, we also want to make the context information that we disseminate independent of the network entities to which they relate. So rather than disseminate context information relating to server X or link X or link Y, the context information is related directly to the content. So it's a slightly different philosophy from the traditional IP approach, where things are related to location. No, here it's related directly to content. And we try to address the scalability issue here through Bloom filter aggregation. So if we've got a number of contents at a server, we can represent those content IDs using a Bloom filter. Now, very briefly, Bloom filters are just a way of representing a set of objects in a very short bit string. But there's a cost to pay for that, and that when we perform lookups of the objects in this Bloom filter, there could be a probability that there's a false detection of content objects. So in that case, there could be, let's say, a non-optimal routing decision. But typically, that's only a very small, so 2%, happens on 2% of the cases. But if we look at the advantage that a Bloom filter gives, we can, say, reduce, in the experiments we've done, 3 megabytes to 100 kilobytes. So when we disseminate this information through the network, we can do it much more efficiently. And then to this Bloom filter, we attach some network context information. And this would be updated hop by hop. So we can add, for example, the resources of the server, the path bandwidth, and number of hops. And then we disseminate this to the network. So the network now is able to make a mapping between content and its context. So in every router there would be a routing table, but this would be a content routing table, not an IP routing table. And routing would be done hop by hop, so that eventually the best content source would be located. So each router or content router would process the bloom filter to determine what content IDs that context relates to, and then update the entries in the content routing table accordingly. And this would be done, say, every 15 minutes, or based on changes in the router, in the server status. And based on this, we've been able to increase significantly the number of content requests that are admitted into the network and successfully resolved. So the top line here is our Kane approach, and this bottom approach is just a standard shortest path routing. And we can see that as the traffic intensity increases, the routing performance, or the amount of requests that we can resolve are significantly reduced. And similarly for maximum link utilization, we can achieve much better maximum link utilization, so better load balancing across the network compared to the shortest path scheme. And better server load balancing. So here the Kane has better or less varying loads across the different servers in the network compared to shortest path. So that's in the fixed network, but how can we apply this in mobile scenarios? So particularly in the RAN part here. So the problem is we can't keep throwing capacity at the problem. As number one, it's expensive, as we know, and it's physically constrained. So there's only so much we can do to increase capacity. So there needs to be some more intelligent, let's say, way of doing business in 5G. A good analogy of that is what they did in the Victorian times. So if for any pipes, you know the Victorian sort of engineering was very clunky, very thick walls and all this. So for pipes, they would tend to crack. They would find that they would crack with time. So how they go about fixing that? They would make them thicker. But actually, they found that it didn't really solve the cracking in the very long term. So eventually it would crack, but and it was extremely expensive. So now, as engineering improved, we're looking at better material design and making more efficient use of resources, and that's really the same sort of mentality that we want to approach 5G with. And the other thing is that increasing capacity doesn't necessarily reduce latency. So we've still got the latency problem that we have to address. And that's obviously a very big contributor to performance. So, as we know that TCP throughput is actually heavily influenced by RTT. So, as RTT increases, the actual throughput will reduce quite significantly. So these are just some basic experiments we did, and they're known experiments and known results. But with, say, a 20 megabit per second link, larger downloads are, the smaller file sizes are heavily affected by the RTT, because most of the time we're spending in slow start. With higher file sizes, that effect reduces, but with content typically being quite small in nature, even in video traffic, it's typically quite small. And so and I'll explain why it's quite small. So this has quite a big problem because we're not utilizing resources as much as we could. And we can see the same thing here. We increase the bandwidth by 5 times, and we can still see the same exponentially decreasing throughput for smaller file sizes, file size downloads. So this is why, for video applications, it's quite TCP and TCP performance is quite a critical issue. So a lot of the video standards now are moving towards having a DASH framework. DASH is dynamic adaptive streaming over HTTP, and this is a more client-driven approach to video streaming. So rather than setting up an end-to-end connection for the duration of the video stream, we set up the connections on demand for each segment download or segment stream. So the video itself will be broken up into segments, and these are independent of each other, and would be, say, 2 seconds in length or 1 second in length, whatever is appropriate. And it can also be broken down into layers. So these layers can be added, for example, to get a high quality video. And then at the user side, the video is adapted up and down based on the bandwidth or the conditions of the network. So if it sees the bandwidth is quite low, then it will start to adapt to a low quality, and then with time, if the bandwidth improves, then the video quality will improve, and so on. So here, these layers can be typically a few hundred kilobytes, maybe up to a megabyte or 2. So TCP throughput has quite a big effect on video streaming performance. So here is a video streaming session, let's say, and we can see here that the segment size, which is in the red, is correlating with the TCP throughput achieved throughout the session. So we don't want this kind of behavior. We want to be able to control this throughput that we have. We can guarantee it more so that we have less fluctuation of quality in the video. So this first part is the initial buffer filling stage, where the buffer is being filled quickly, and we can see that actually the effect of that is to increase the throughput, but that's early at the beginning. And then, as you can see, slow start is being performed at every segment download. So we need a more efficient way of doing this. Now, there have been ways of improving TCP, but what we're looking at is actually bringing content closer and making the network itself play a bigger part in content delivery. So if we look at the latencies between a UE and a content source, we can see this breakdown of latencies. So typically between the UE and the eNode B, you get 10 to 20 milliseconds. So, but from the eNode B to the PDN gateway, it's 5 to 20 milliseconds. So we're already in the 40 milliseconds by the time we get to the PDN gateway. And then if we go through the internet, then we've got a very variable delay, which can vary from 20 milliseconds up to a few hundred milliseconds. So we've got a big unknown in the internet, and that's why there's a motivation to bring content closer to the user. So how do we improve content delivery performance in 5G? As we said, so bringing content closer, but also making more efficient use of the resources we have. And a lot of that will be driven by context information that the network collects about the user in terms of its mobility, in terms of its application status. So if it's a video application, what the status of the buffer is at the user. All this information can help drive efficient content delivery to the user. And a large part of that will be, let's say, assisted by a network function server, or as the first presentation put it, as a user agent. So they're similar concepts. And this would be placed south of the server gateway. And so in Etsy, for example, they call this the mobile edge computing server. So these are really the same concepts. And the point of the NF server would be to monitor and predict the RAN, EPC, and UE context information. So from the RAN side, we can look at the signal strength of the users, the bandwidth, latencies, packet error rates. From the EPC side, the bandwidth, latency, and packet error. And from the UE context, we've got various fixed parameters or fixed context information, so the screen size of the users, the resolution of the video they're watching, or their screens, and the mobility of the users, how fast and what sort of general profiles of mobility they have. Is it random? Is it quite steady? This kind of thing. And based on all this context information, the aim is to perform smart content handling. So things like prefetching content. So if the user is watching a video, then we can prefetch segments it's likely to watch after that. Or even cache the content so other users, so if it sees a demand for the same content, then to cache that content to improve the content access latency for other users. So the RAN is quite a good place to put this NF server because it can provide an aggregated view of the UE context. So decisions that the NF server makes are done with the interest of all the users. So it avoids this greedy UE problem. So how do we use this context information to enhance user QE? Well, I'll go through a number of use cases, and these are research that we're carrying out at the 5G Innovation Center to give a flavor of what areas we're pursuing. So the first case is in accelerated video streaming. So here the NF monitors and predicts the UE and RAN context, and then will periodically report the predicted context to the content server. And here it can influence the TCP behavior of the server to match the RAN conditions, so that we avoid the need to do slow start every time we request a segment. The second use case is a bit more intelligent than this. So it takes the context information, and so if the UE is requesting a certain video quality, and the RAN itself has context information from the EPC and knows that the EPC can't support that quality, so what it would do, it would remark the request before sending it on to the content source. so load and be able to determine where best, for example, to download that object from. So what about actually the wireless part? So we've looked at within the north of the eNode B, but what about south of the eNode B? So how can we use context information to improve efficiency of the content delivered there? Again, two use cases we'll look at, or we are looking at. The first is multi-rack content delivery. So how can we use multiple racks simultaneously to boost the available resources? And the second is D2D communication. So in the multi-rack scenario, we want to be able to use the racks simultaneously. So today we use the racks in an either-or approach. So if we're connected to Wi-Fi, then we use Wi-Fi. If not, then we resort to cellular. But if we use them simultaneously, then we're able to boost the overall bandwidth available to the users. However, if it's not done intelligently, then we found actually that can lead to more detrimental results than if you were to use the either-or approach. So, and the reasons for that is because the different racks will typically have mismatched throughputs. So if we're not coordinating when we download different segments, then we can lead to buffer stalling and that kind of thing. And also, when it's not done intelligently, then the UE will be using the resources of macrocell, for example, to download content whereas small cell or Wi-Fi would have been sufficient for that purpose. So we're essentially stealing resources from other users unnecessarily. So the whole system becomes a bit unoptimized. So we want to use a context-driven approach to be able to predict future user connectivity and throughput, and to be able to schedule the content requests over different racks so that content can arrive on time, and the video playback will be smooth, and the users will be happy. And we can assign, for example, more critical content to more stable racks. So when we have the layered approach, where the layers, one layer is dependent on the layer below it, then we can assign the lower layers to be downloaded over more stable racks. And the other use case is in D2D communication. So here we've got a client which can be in a so-called NOT spot, so it doesn't have any coverage. Or it could be at the edge of connectivity. So here the NF can help in providing or allocating a helper to the client, and one that would be able to relay data, so it will be in the vicinity of the client, and will be able to relay the data it's requesting to the client. And so the NF would be able to, for example, know the helpers and the client's predicted mobility, so that it can choose a helper that would stay in the vicinity of the client for the longest period of time. And it'll be able to look also at the application requirements of the client. So what about other open research issues? So ICN really is, because it's content-based, so IP addresses play less role in how data is delivered. So when we request for a particular content, the content is delivered to the user without the network knowing too much about the mobility of the user. So the network would be oblivious to the client's IP address. So there has to be some reconciliation between the content side and the network side. So the network itself would know the IP address, but if the branching point is outside the mobile network, then how is that reconciled to the user? So, whereas if the branching point is inside the mobile network, then that wouldn't be an issue so much. And the other point actually is about context collection and dissemination. So this is quite an important part about how is context information collected. So what protocols are developed to support the context information collection from clients, from EPC and RAM, and how frequently it's collected. So from a UE, if it's delivered too frequently, then we have a strain on battery. If it's not frequent enough, then obviously we have the context information being not very fresh. So we need to study the balance between the two to optimize the delivery of content to the user. So finally, to summarize, the key question we have to ask is how can we capitalize on context and content awareness to improve the operational efficiency of the network, increase its capacity, and improve the quality of experience, ultimately improve the quality of experience. So content networking is all about how can we improve the quality of experience by bringing content closer to the user and optimizing how it's delivered. And we looked at this network function server, the RAM, so how that can collect and disseminate context information, and essentially have local applications in the NF to increase content delivery performance. So much like the model that Reza from the University of Bristol presented yesterday, where we have, like in the phone, we've got apps. Similarly, in the NF, we also have apps. So one of those apps could be video remarking application or context assistance application or something along those lines. But really, I mean, we've presented, I presented 5 use cases, but I mean, the possibilities for NF-assisted content delivery are potentially endless. Thank you very much.
All right, we have some time for questions to the floor.
You spoke about this NF functionality as this network function server at the run. Can you clarify a little bit more where you would place it in the run? Is this a centralized function in the run, which would be somewhere at an edge cloud, or is this a distributed function, which could be also closer to the antenna, or what is your view there?
Well, I mean, the actual position can be quite open to research. So depending on how much resources it can have and the kind of applications it's running. So if it's quite resource-intensive applications, then obviously that would need to be brought down closer to the user. Whereas it really depends on what the applications are.
Then I have a second question. You always spoke about content delivery. Do you also consider content processing location somewhere at the run? Because we have in 5G very stringent latency requirements in some areas. Is this also something you investigate?
No, it doesn't.
Because the content delivery for content, which is interesting for several parties, could be, let's say, bandwidth, but it doesn't help in the latency situation.
Yeah, exactly. I think this is a view taken by many, that it's not efficient to put processing in the network. So, for example, with Dash video, the server itself would be able to, would have many representations. So even the server itself wouldn't do the processing on the fly, whereas it would have various representations of the video ready to be sent based on what the user is requesting. So even in the server, this is not the case. So if it's not in the server, then I don't think it's wise to put it in the network either.
Yeah, but when you're looking for tactile internet situations, it might be helpful to have a content processing closer to the antenna.
Possibly, yes, but I'm saying for video applications, our focus is really on video applications. And,
okay, thank you.
I think that would be.
Okay, so thanks for the interesting talk. I would like to know more about the, maybe from my understanding, the routing. You said there's a possibility of shortest path routing. I'm a bit wondered because how do you do this? Do you have knowledge where the content is on every node on the network? So this is, I think, not scalable. At least I would learn to know how routing can actually work in the content-centric networking.
4K, so 4K how context.
Yeah, so you know in IP networks we have the longest prefix match, so you can aggregate, and here you should, I think, need some sort of aggregation to have a manageable routing table, so to say. So, at least from my perspective, that was the biggest problem in this content-centric networking idea space.
You're not alone. So, I mean, yeah, this is a big issue for ICN in general. But, I mean, so what Kane, for example, has tried to do is increase the efficiency of the transmission part, but we haven't really addressed
the routing problem
entirely about the content table size. We've got ideas of how to improve the speed, but not to reduce the size as of yet.
Okay.
That's still an open.
So, in this sense,
the thing is, sorry, if I could just interrupt, so the prefix base, you mentioned about content prefixes. So this is proposed in NDN, actually. So we have a server and then a certain subcategory of content, etc. But I think there's a lot of debate about this as well, about how that can work, because if one content is moved from one server to another server, then immediately that whole prefix tree has broken. So.
Okay, and just to follow up, what is your personal opinion whether this content-centric networking paradigm might at some point in time be a viable successor of IP networking? So we had the internal discussion, I think 2 years ago, whether internal develops, whether this would be a viable option for 5G, but we were a little bit because of this routing problem. So a successor of IPv6 now that it took 25 years to somewhat introduce IPv6, and now we're coming up for 5G, starting with content-centric networking, replacing the IP routing stuff. And what's your view? Because you are in this field, do you think it might be possible to evolve it to the point where it can be a successor to the server host stuff networking kind that we are currently having in the internet?
It's difficult to say about commercial uptake, to be honest. I'm sure many people in the ICN community would say the same thing. But I know it is actively pursued. For example, in Cisco, this is quite a hot topic of research in Cisco. But I guess compromises could be made about, so in terms of, for example, what we did in Kane is to have bloom filters. Well, with bloom filters we have a 2% false positive probability. So we're sacrificing a bit of routing performance, but for a bigger gain elsewhere. So in the same sort of stream of thinking, there could be compromises in terms of, I don't know, again, routing performance or other areas.
Thanks.
Yes. I would like to know if this use cases deals with the secure connection, I mean, or application, the application level. I know we are in a trend to have more and more secure connection when we get to download going to share Google or whatever we are interested in this. I don't know, do you take into account this?
I'd love to claim I'm a security expert, but I can't. We're not really active on the security side of things. So obviously this has to be taken into consideration. And I agree it's important, but
so the network function that does not deal with the content that is actually created. It's not a network function that is delivered by the service provider.
Sorry, say again.
I don't know how to explain. So the whole point is you need to be aware of what is going through the network to get the network function to deliver the content. So somehow it is required that the service provider provides this information if it is encrypted. So there is a whole point.
HTTPS is a general problem. As you want to be content aware, and then everything is HTTPS.
And the whole point is that it's a whole trend to discuss on the 5G to how to deal with this.
All right. Okay, last question, and then I think Marcus will be the one.
Thank you. It was a wonderful talk. My question is, basically the network is learning about who wants what, right?
Sorry, I didn't catch.
The network basically wants to learn who wants what in this chain architecture, right? And it's happening in two levels. One is at the mobile and other is at the fixed network, right? Isn't there, will not there be a contradiction because you have multiple users connected to different mobile networks served by a common fixed network, and it's very much possible that different people access same data and it results in multiple copies being generated throughout the fixed network.
I mean, caching as well, again, it's something that requires active research on. So, for example, cache coordination, that's a big topic in RCN. And how we, there's obviously the very simple solution of cache everything everywhere, which is quite efficient actually, but don't forget as well that content popularity follows a heavy tail distribution. So the popular contents will be quite a small subset of what users request in general. In fact, based on some experiments we did with BBC data set, we found that 95% of requests are for 5% of the content base. So even with cache everything everywhere, it still gets very good gains. But if you want to improve it, then we need cache coordination.
So following the question, so has Kane accounted for load balancing? Like as you said, there can be multiple requests on the same content item, and if the content item is going to be nearby me, and 4 users of the same, let's say, access point is going to access the content at the same time, does your architecture support it, or have you worked on it?
And so to advertise about cache content, is that what you?
Yeah. Let's say a viral content, and and you want to be like have a load balancing. Do you have a load balancing scheme or not? That's
so in Kane, yes. That's so. For example, when we resolve the request, we look at the different metrics that we want to prioritize. Let's say, so if we want to prioritize server load, we choose a few servers which are close, are within a certain threshold, and then out of those servers, we choose the least cost path, for example. So that's how we achieve load balancing. Okay, if you want, we can have offline discussions.
Okay, then let me take thoughts again. I would like to ask Marcus here, Mark. I think we have a couple of minutes left, and maybe we can address some of the topics that were actually mentioned in all three presentations. Absolutely.